So as I mentioned in the previous part of the lecture, one of the problems with the direct mapping is that there is only one location in the cache for each one of the memory addresses. So if I happen to be accessing two memory addresses that maps to the same location in the cache, I will be having constant conflict between those two accesses. One will be replacing the other and causing cache misses. And I could have the situation where in the extreme, I could have a program that's only using one of the blocks in the cache, and the rest of the cache is completely empty, and is still, I keep having a miss every time that I access any of the positions that the program is accessing because of a conflict in that single block in the cache. So in general, I would like to change the mapping to allow a given memory address to be mapped to more than one block in the cache. So the way I'm going to do that is by grouping the cache blocks into sets. So what I have done now, I have grouped two blocks in each set. So I have this blue boxes here that indicate that I have two blocks in each set. And I still have one valid bit in this case for each of the blocks. And I have one tag for each of the blocks, but I have two blocks per set. So this cache stores 4 kiloblocks. So how many sets are in the cache? Obviously, if I group 2 per set, I'm going to have 2k sets. That's half as many as the number of blocks. And now I want to give a unique number for each, a unique ID for each one of those sets. How many bits I need to give a unique ID for each of the sets? Well, I only have 2k sets, so that will be 2 to the 2 to the 1 will be 2 times 2 to the 10. So there will be 11 bits. I need 11 bits to identify each one of the sets. So notice that because I group my blocks into sets, and now I identify each set individually, the number of bits used for the index has been reduced by 1. Before, for the same size of cache, I needed 12 bits to index each one of the individual blocks individually. Now I need 11 bits to index each group of 2 blocks. And I will be introducing this notation now. So if I have the address 0xFF000018 that I wanted to check whether it's in the cache or to store in the cache, the tag now will contain 17 bits because it will be the 4 bits that I have for the offset plus the 11 bits for the index. That's 15 bits. There is 17 bits remainder. So instead of writing the 17 bits as a 17-bit number here, I am introducing this notation that I created. What this notation tells me is that the first 4 digits here are hexadecimal digits. So each one of those digits represent 4 bits. Then I have the underscore, and to the right of the underscore, I have binary digits. So each one of the digits to the right of the underscore represent a single bit. So this tag here has 17 bits, 4, 8, 12, 16, plus 1, 17. This is a notation that I created. I haven't seen this in any books or anywhere else, but it's a notation that's convenient when you're discussing cache design, because I don't need to write the 17 bits. So if I look at my address 0xFF000018, I will take the 11 bits that I need for the index, and then the tag for this allocation to the cache is 0xFF00 and this bit 0. And the valid bit is 1, indicating that the address, the block from that address is in the cache. Then I can take the lower 4 bits to find which is the word that I want to index in the cache. And this tells me that I'm accessing this word in this block in the cache. If now I do an access to the address 0x80008018. What will gonna happen is I'll take the 11 bits. That takes me to the same set. So I am in the same set, but now I can have two different blocks in the set. And indeed, the second block in the set is the block at the address 8000 and then a 1. And the offset is 8, so the second block is in this position. This way I can have I can have each location of the memory, the FF000018 and the 0x800818 in the cache in two ways. There are two possible blocks in which either one of those addresses from memory can be. So we can say that each location can be in a set in two ways. So we call each one of those blocks a way in the set. So the FF008 could be here or could be here, and the 8018 could be here or here. So we say that this cache is a two-way set associative cache. And that's the term that's used to designate that there are two blocks per set in the cache. So now if I am giving the address 0x7900014 and I wanted to see whether that address is in the cache, what I'm going to do, I'll take the index and I'll find that if it is in the cache, it has to be in this set. So what I'm going to do now is to take the offset, so this will be this word, but before I can return the word, I have to check to see if it's a match with the tag that I have in the set. So the tag in the address, that is 79000, does not match either of the tags that are in this set that was identified by the index. Therefore, the word that the processor wants is not in the cache, and I will report that this is a cache miss. So now this illustrates that for each access that the processor does, I have to do two tag matches, one for each one of the blocks in the set. And of course, we can now that we have a miss, we're going to have to go to the lower level of the cache and we're going to have to bring the block that the processor wants. That's the block 0x79000014. And we're going to have to put that block in the cache. But there are two ways in which I can put that block in the cache. I can put in the way 0 of the set, or I can put in the way 1 of the set. Which way I'm going to use? The question is, which of the two blocks that are currently in this set that should be removed from the cache to make room for the new block that the processor has replaced? You could think of several different policies to do that. You could think about first in, first out policy, last in, first out policy. But the policy that is the best policy for caches is the one that says that I'm going to remove the block that has not been used recently. So the block that the processor has not accessed recently is the block that should be the candidate to be removed. So, but the question then is, how do I know which one of those two blocks has not been accessed recently by the processor? In order to maintain that information, I'm going to need one more piece of information in my cache. That is the least recently used bit, or the LRU bit. So I'm going to add one more bit to my cache design. There will be 1 bit per set. That will indicate which one of the two blocks in the set has not been used recently. So we associate the least recently used bit with each set of blocks. And we have two ways. We have the way 0, in this case is drawing on the top in the slide. and we have the way 1 that are the ways draw in the bottom of the slide. So the least recently used bit will be the bit corresponding to the way that has not been accessed recently by the processor. So let's see what the least recently bit state should be. Let's suppose that the processor reads the value from this memory address. In this case, when completing the read, the processor or the cache will change the status to point to the second to the way 1, because the way 0 has just been recently used. So the way 0 is the most recently used one. The least recently used one is the way 1. If now the processor reads the address 0x8018, that's this green box here, then the cache is gonna change the status of the least recently used to be the 0. If now the processor reads another address that maps to the same set, and one of them has to be replaced, the one that will be replaced is the least recently used one. So we'll replace the block 0, because the least recently used bit indicates that the block 0 has not been used recently. So that what was the red block that was there has been thrown away, and I have written over this the purple block here that is at the address 0x79000014, and I will update the tag associated with the block indicating that this is the new address that is stored in the cache. So the higher associativity in the cache allows me to have multiple blocks that would otherwise conflict in a lower associative to be present in the cache at the same time. So let's see, how do we relate the associativity of the cache with performance by looking at one example. So let's consider that I'm executing this piece of code here. There is a loop, and there is a jump here that goes to this position here, and then when I get to this position, I jump back to the loop, and this is a branch equal that goes to the false position. And let's assume that I'm executing this program in a directly mapped cache. So if and you need to pay attention to the addresses that I have here. The addresses on the top have the number 0x8000, and the addresses in the bottom have the number 0x8001 in the beginning of the address. Of course, this example is a contrived example that has been constructed to illustrate how you can have conflicts when you have a directly mapped cache. So if I start executing this program, first I'm going to be fetching at the address 0x80000020. So we're going to run a simulation of the cache here to understand what's going on. In this case, I need 12 bits to find the corresponding block in the cache. So I'm going to take the 12 bits corresponding to the index. I'm going to find out that the access is to this block in the cache. And then I will, the valid bit in this case is 0. I'm starting my execution. So it's a cache miss. I'm going to go to the lower level in the memory hierarchy. I'll bring the entire block, not only that word. When I go to the lower level, I bring the entire blocks. So I'm going to bring 4 words from the lower level. And I'm going to write my tag. And let's say that those are the words that I brought from the lower level. And my offset here is 0, so I'm accessing the word 0. So I'm going to be accessing this word into the cache. Next, I execute the branch equal instruction. Note that the branch equal instruction will be a cache hit because I'm accessing the address that's immediately after this one. So I'm accessing now this word, which I already brought when I had a miss for the add instruction. So that's a hit. And next, I go into the false label, and I am accessing now at the address 80010020. So again, I take the index, I go to the same block as before, and now the tags do not match. The value bit is 1, but the tags don't match. This tag is the tag 0x8000, and I'm looking for the tag 0x8001. So this is a miss. I need to do a fetch from the lower level in the hierarchy, and I need to replace this block. So I will replace the block. I'll put the new block in that has the tag 0x8001. There will be the code for the instructions in there. I'm gonna then execute the move instruction, and then I'm gonna execute the jaw instruction, which is the word right next to it, so that's a hit. And now I go back to the beginning of I jump to the loop, and now I need that add instruction again. But of course, the add instruction now is gonna be a miss because I have replaced the add instruction when I fetch the move instruction. So this is an example where the entire cache is empty. There is nothing else in the cache. The only thing that I have are those instructions. And I'm gonna be having many cache misses because every time that I go to this area of the memory, I overwrite the instructions that I had fetched when I was in this area of the memory. So that obviously is not an efficient use of the cache, and the problem is that I have a direct mapped cache, and I was unfortunate to have this miss between these two areas of the program that I'm executing frequently together. We're going to try to fix that by having a higher associative to the cache. So now my cache has 2 blocks per set. And now I'm going to repeat the execution. When I fetch the first add instruction, I'm going to use not the 12 but the 11 bits to find out which set, because remember I now have grouped the blocks into groups of 2, so I only have 2 to the 11 sets. So I find the set, and in this case both of them have 0 for their valid, so I know that it's not in the cache, so I'm going to get a cache miss. I'm going to fetch from the lower level, and now I'm going to store that block into this way into the set, in the way 0 of the set, and I'm going to annotate with the tag 0x8000_0. I'm going to execute the branch equal instruction, which will be, so I execute the add instruction, I follow to the branch equal instruction, which is going to be a hit because it already came with when I brought the 4 words for the previous fetch. And then I go to the false label, and in the false label, I need to fetch now the word from the address 0x80010020. So again, I do the mapping into the set, it maps to the same set. I check to see whether it matches the tag of the way 0 here. It does not match. The way 1 has a bit, an invalid bit, therefore it does not match with the way 1 either, so that's a cache miss. I go to the lower level of the memory hierarchy, and I bring the 4 words that form this block, and I write the tag into that position. And now I can execute the move instruction. It will be a hit. And by the way, if I go back in the slide a bit, notice that when I do this access, that I store that new word into the way 1, I changed my list recently bit from 1 to 0, because now the list recently used way in the set is the way 0. So then I provide the code for that instruction to the processor, and when I execute the jaw instruction, that's a hit. And then when I move back to the loop and I access the loop, I also have a hit because I have not overwritten that block. So this illustrates how by changing the cache from a directly mapped cache to a 2-way set associative cache, this simple program that was giving me several misses just for the execution of the instructions because of the unfortunate conflict between the instructions in this part of the program and in this part of the program for the directly mapped cache, when I change it to a 2-way set associative cache, those misses no longer occur, And that is an illustration of how increasing the associativity can improve the performance of the memory system.